Hi everyone, welcome to our talk. And today we're going to talk about various aspects of physical simulation and AI, and especially on the differentiability aspect of how to do differential physics and how does it help artificial intelligence. I am Yuanming Hu from MIT CCL. I am a fourth-year PhD student there. So before we start, let me briefly introduce what is forward physics simulation. Let's say you have a basketball, you want to throw it. In this very simple case, let's assume we have zero drag. You can accurately predict the final position after time t, x sub t, as a function of various physical parameters. In this simple case, you can have a very simple analytical solution for the final position. However, the practical problems are often harder and it's often not possible to solve analytically. So that's why people usually use numerical integration to move forward in time and do some prediction. Real-world physical simulation is usually more complex, and here we have 3 water wells interacting with water, and this is a SIGGRAPH 2018 paper that we did. And we can use the same simulator for simulating a robot, and by doing this, we can validate which robot design moves faster than the other. We can pick the optimal design without actually manufacturing the robot, which accelerates the development of robots. And sometimes physical simulation can actually scale to very, very large scale. And here is a simulation of over 100 billion particles. As you can see, a lot of Taichi letters falling down. And Taichi is a programming language that I'm going to dive into later a little bit. So that's for forward simulation. What is backward simulation? It's actually pretty easy as well. So before we start doing backward simulation, it's important to define a loss function. And here, let's define loss function to be something like the square distance between the target position xt star and the final position xt. So after defining the loss function, one natural question to ask is it possible for us to somehow compute the partial derivative of L with respect to x0 and partial L with respect to partial v0? And it's actually not hard. You can just use the chain rule, or some people call it backpropagation or reverse mode auto-diff. And by doing this, you can just accumulate the gradients all the way back from the final state to the initial state. And then one important application is to use the gradient to do some optimization so that you can somehow align xt and xt star. Basically, that means moving the basketball into the basket. So apparently, differentiable physics is not new, and gradients of simulation for optimization is well studied in computational physics and mechanical engineering for many years, actually. And recently, the ML community is very interested in somehow combining differential physics and artificial intelligence. And the key to achieve this is to develop various differentiable time integrators so that you can have a time series of simulation, and somehow the time series of simulation can interact with neural networks or other deep learning modules. You can combine them in whatever manner you want. And the time integrators have 2 families. The first family is what we call explicit time integrator, one example being symplectic Euler. In this kind of time integrator, using normal reverse mode auto differentiation usually gives you reasonable behavior. Sometimes, maybe because the system is too stiff, you have to use an implicit time integrator, or you're just solving for a quasi-static state. In those cases, you have to leverage the adjoint methods. And basically, the adjoint methods are doing differentiation under constraints. The constraints are usually linear or nonlinear system to solve. Gradients of simulation is well studied in mechanical engineering. One typical example is what we call topology optimization, and there's a very well-written book on this. But for today, I'm just going to talk about a very basic concept of topology optimization. So by doing topology optimization, you're distributing limited material in a structure to minimize deformation under external load. And then, of course, you need to somehow use the adjoint method to compute the partial derivative of the loss function to the topology. Here, we have to use the adjoint method because you have to solve for the displacement under the external node, which is a linear system solve. And here I'm showing you a bird-big topology optimization example. I'm showing the optimization process from the initial guess to the final optimized structure. As you can see, this gradient-based optimization can really be powerful, and it gives you very fine detailed structure within this very big structure. That's for differentiable physics for more classical applications. Today, the focus is going to be differential physics plus AI. So if something like this work, what can we do? We can do a lot of things. We can somehow learn neural network controllers much faster than reinforcement learning. This is really attractive. And we can do robotic topology and actuation co-design, which means you're not only optimizing for the controller, but also optimizing the robot geometry. You can also do system identification that somehow measures physical properties of a module in your robot by watching a video. You can even try to reduce the sim-to-real gap by hybridizing simulators and learning, because now you can hybridizing simulation modules and deep neural networks into a single system and train it end-to-end. So before we start, it's actually there are actually a lot of questions to ask. Clearly, there are many issues to address because this is a relatively new combination, but today I'm going to focus on 3 questions. The first one is what happens on more complex systems and longer time horizon. Previously, we just saw like if you just threw a basketball or you're solving for a quasi-static state under external load, differential physics works pretty well. But what if the systems gets more complex, or you have thousands of time steps, you have a very long time horizon? The second question we have to address is practically how do we actually write a differentiable simulator? This is a really big productivity issue because there doesn't seem to be a good tool for you to write differential physical simulator. We'll come back to it in a minute. Finally, how does a differential simulator run efficiently? Do we have a existing framework that allows it to run very performantly, run very efficiently, or not? Clearly, the answer is no, otherwise I won't be raising this question. So let's now talk about the first question, which is, what if we have more steps and more complex system? The natural question to ask here is, do long time horizon simulation gradients even make sense? Because, you know, the world is chaotic. What if for a simple system, it's easy to somehow evaluate the gradients, but what if we add more frictional contact? What if we have thousands of degrees of freedoms? What if we have elastoplastic deformation? And in order to make it work, or in order to make it meaningful for AI, we have to somehow introduce actuators, and we have to plug in neural network controllers. All of those factors are introducing a lot of noise or chaotic behavior to the system. We have this famous Lorentz attractor example here. As you can see, sometimes people call it butterfly effect, meaning the end result of a simulator can be very, very sensitive to the initial configuration of the system. In other words, the physical world can be very chaotic. So if you represent the computational graph of a differential physical simulator plus neural networks, you will end up a graph with billions of nodes. If you look at this graph, let's say we have 2,000 time steps, and in each time step, we have a bunch of physical states, and then we feed the physical states to the neural network controllers. In the controllers, we evaluate, let's say, 2 fully connected layers, and then the controller gives you a control output, which you can consider as the actuation to the system. You feed the actuation to the differentiable simulation, and then usually a differentiable simulation can have thousands of mathematical operators, and it's not hard to end up with tens of millions of nodes in a computational graph. Is this graph still numerically stable when evaluating the gradient? And the second question to ask is, running this graph on an existing system such as TensorFlow, is it going to be efficient? So those are really interesting questions, and that's why we developed this chain-queen simulator. This is a paper at ICRA 2019. We proved that it's actually numerically stable. The gradients are actually good enough for optimization, which is a great news. And secondly, we find that existing systems such as TensorFlow isn't efficient enough for differentiable physics. Essentially, in chain-queen, you can somehow use the gradients to do a lot of optimization to make your robot move in your desired direction. Chain-queen is a differentiable physical simulator for deformable objects. So this is pretty attractive because nowadays a lot of people are very interested in soft robotics, where every part of the robot can actually deform in an elastic manner. The chain-queen physics engine is based on the recently proposed moving least squares material point method, which is a simplified and more efficient version of material point method in graphics. Unfortunately, when we were doing chain querying, we didn't get a very powerful tool that gives us both performance and gradient evaluation. So we have to manually derive all the gradients on our own and implement the kernels using CUDA, which is not really pleasant. So if you look at a single simulation step of chain querying, it's basically just a usual material point method simulation. For the forward, you just do particle to grid operation and grade your particle. For backward, you're just executing all the kernels in a reverse manner so that you can accumulate the gradients from the final state to the initial state. The whole simulator can have usually hundreds or thousands of time steps. We implemented everything using CUDA on GPU, and let me show some applications. Here's a system identification example. Let's say we have two balls, A and B, and A collides into B, and then you have an observation that B ends up with C, and we're trying to solve what is the relative density of A and B. Initially, if you set the density to be 1, then unfortunately there's not enough momentum after the collision for B to reach destination C. So after a few rounds of gradient descent optimization, you may end up with a relative density 2.26, which gives B enough momentum after the collision to hit the destination C. So as you can see, by using the gradients, we can know how to adjust the relative density of two balls and then end up with a reasonable guess. Maybe more interestingly, we can use the gradients to optimize controllers. And here we are optimizing a 4-leg 3D robot. As you can see, each leg of the robot has 4 actuators, and the actuators are elastic, and it can either contract or expand. And by somehow contracting and expanding the elastic muscles, you can somehow just make your robot move forward. This is a simple 2D example. You have 2 legs, and each leg has 2 actuators. Let me just show you how the optimization actually happens. This is iteration 0, and as you can see in the very beginning, the robot does nothing. And after 30 gradient descent iterations, the movement already starts to make sense. It's moving very slowly to the right. And after just 58 iterations, you can see it's moving and jumping very happily to the right. So this is actually a very efficient learning process compared to reinforcement learning. Here I'm showing 58 iterations of the optimization process. As you can see, starting from iteration 0 is not making progress, but after just 58 iterations, it's starting to behave very smartly, just by brute force gradient descent. So this is a 3D quadruped runner example, and it has 4 legs and 16 actuators. The same thing, 0 iteration, 50 iterations, and then 120. Finally, 200 iterations. You can see this cute robot jumping to the right. And here's a robotic arm example, still optimized using gradient descent, and then the controllers are neural networks. You can see it's very rapidly to learn to reach the blue destination using its tip. Here's an open loop controller example with a crawler, and the crawler is just crawling on the ground to move to the right. As you can see, surprisingly, even with an open loop controller, the learning can happen very smoothly, and it actually takes only 14 iterations to move, to make it to learn to move. Here's a relatively quantitative example where we compare our brute force gradient descent against the state-of-the-art reinforcement learning algorithm by that time, and you can see it's almost 1 order of magnitude faster convergence. As I mentioned, sometimes it's meaningful to co-design the robotic geometry or elastic behavior and actuation sequence. Here you can see we are designing a robotic arm with different Young's modulus on different regions, and as you can see, by combining the optimization of Young's modulus and actuation sequence, it can learn to somehow reach the destination. without a Young's modulus optimization, reaching the destination would be very, very hard in this case. So our conclusion in this work is that gradient descent really works, and the gradients can be really stable. And regarding performance, we find something very interesting, which is handwritten CUDA, which is a lot of engineering, actually runs over 100 times faster than other systems such as TensorFlow. So this is maybe not surprising, but a very important message during this work. I'll talk about why TensorFlow is slower in a moment, but now let's just focus on a high-level view of this problem. So you have a trade-off between productivity and performance in developing differentiable physical simulators. You can either abuse TensorFlow, or you can handwrite CUDA kernels, and you cannot get the both words, the benefits of both words. Like TensorFlow gives you auto differentiation, but it's very slow for writing simulation. CUDA kernels are high performance, but you have to derive the gradients manually, which is a really painful process. The question is there a way for us to somehow easily write high performance differentiable simulators? Well, in order to solve this question, let's first discuss why is TensorFlow not suitable for writing differentiable simulators. The answer is easy because it's not designed for physical simulators. Instead, it's designed for deep learning, and deep learning and simulators have very different computational patterns. So for example, physical simulators tend to use densos or gathering scattering operations. It tends to have fine-grained branching and loops. So those constructs are pretty common in simulator, but they are not easy to implement efficiently in array or tensor-based languages such as NumPy or TensorFlow. So now we know the reason why TensorFlow is not good, because it's not suitable for, it's not even designed for physical simulators. So the solution is clearly we need to design a new system for physical simulator. That's why we developed the Taichi programming language. We published the result on State of Asia 2019. And essentially, Taichi is a high-performance domain-specific language embedded in Python. And we have a JIT compiler written in C++. It has multiple backends. You can write Taichi code in Python, and then it will run it on multi-thread CPU or GPU, just as TensorFlow. Taichi is more specifically designed for graphics simulation and more exotic AI applications. I mean, those AI components that cannot be easily implemented using TensorFlow. Usually, you have to write CUDA, manually write CUDA kernels for those operators in TensorFlow. But in Taichi, it's very easy to write those. And one defining feature of Taichi compared to TensorFlow is what we call programmable megakernels. Those programmable megakernels allows programmers to write high-performance kernels using just Python, and then more importantly, those megakernels maps to a single CUDA kernel on the GPU. That ensures that we're having very high arithmetic intensity, meaning we're doing more flops per byte. So apparently, Taichi was not differentiable, so we implemented or developed a different system, which we call DiffCVGP. That's a differentiable programming extension on Taichi, and this work was published at IPR 2020. In DiffCVGP, we can easily mass product high-performance differential simulators in a language that is very similar to Python. So this kind of mass production proves that the language has very high productivity. Recall that previously in ChainQueen, we were using CUDA, and that was not very productive. And in fact, we easily wrote 10 different differentiable simulators using DiffCVGP. So here are just 3 examples. I'll show more demos later. So the Taichi compiler is a standalone compiling system. Basically, starting from Python script, we lower all the way down to executable kernels on parallel devices. As you can see, we have a pretty complex compilation workflow that progressively lowers the high-level Python kernel into a low-level executable code. The key language design features of DiffCVGP are differentiable, imperative, megakernel, and parallel. So apparently we need things to be differentiable so that those systems can be used in deep neural networks, and differentiability is one of the key features of deep learning. And imperative is more targeted to physical simulation because people have been using imperative languages such as C and Fortran for writing simulators for decades, and we don't want to enforce people to use a functional language to write simulator. That is less practical. And megakernels and parallelism ensures that we can run the kernels very efficiently. By using DiffTaichi, we can write shorter code, which actually 4.2x shorter code compared to hand-engineered CUDA, partly because now the gradients are evaluated automatically by the Taichi compiler. You do not have to manually derive the gradient, which is really tedious and error-prone. And it also runs over 100 times faster than TensorFlow, just because we're now more tailored for the computational patterns in simulation. In TensorFlow, it may be the case that you waste over 90% of your time just launching kernels or reading from main memory. Please check out our paper for more details on performance and more evaluations. So here's a high-level view of 2-scale AutoDiff in DiffTaichi. So we designed our AutoDiff system to be 2-scale because we really want our kernels to be megakernels, and we use a tape to record the megakernel launches. And then within the megakernels, we do source code transform so that a megakernel's gradient kernel is still a megakernel. This ensures that during gradient evaluation, we're still running high-performance kernels. Of course, there are many related work. Each of them are doing a great job in their own field. But for physical simulation, DiffTaichi is the only system so far we know that serves all the features of simulation. If you use other systems, it's likely that you are going to miss one or two the requirement of physical simulation, and DiffTaichi is really designed and tailored for writing differentiable physical simulators. So let's come back to this figure, and DiffTaichi allows programmers to easily build differentiable physical modules that works in deep neural networks, and the whole program can be end-to-end differentiable. Actually, for this, if you write this computational graph in TensorFlow, it's very easy to end up with millions of operators, and sometimes TensorFlow can stay for minutes or even tens of minutes just to compile the computational graph. But in DiffTaichi, you don't have that issue. It's just because TensorFlow is more designed for deep neural networks, and it's unlikely that a deep neural network can have a million operators, but it's very common in simulation. So the computational patterns are really different in two frameworks. Here's a reproduction of the 2D simulation example. You can actually write this simulator within 200 lines of code, I believe. And of course, DiffTaichi is open source. Every demo I show in this talk can actually be reproduced with a single Python script. You're free to check out the code and then run it on your own to have fun. Here's a 3D version, and then for some reason it's learning to moving to the right in a weird manner. We can also add some water to make the robot's life harder, and clearly it does move less quick when there is water interacting with the elastic material. So here's a mass spring system simulation, and the mass spring robot will learn to move to the right, and we use a closed-loop neural network controller. Here are two rigid body robots. In this example, we optimize for an initial velocity field so that the fluid simulation forms a Taichi pattern after 100 time steps. Oh, this is my favorite one. So we are combining the differentiable water wave simulator with a differentiable water renderer, and then we feed the simulated and rendered result into VGG16. So this allows us to generate a water wave that somehow refracts the background image into something that can fool VGG. Let's check out the results. So initially, this is a fox squirrel image, and VGG correctly classifies this one as a fox squirrel, which is a pretty good job. I don't even know it's called fox squirrel. I only know it's squirrel. And if we add a ripple to the center, you will see what you see in the center image. But more interestingly, you can actually generate a very subtle water wave that somehow refracts the background image into something VGG classifies as a goldfish. This is really interesting. We can use the water renderer to generate something we call adversarial water wave that can fool VGG. But as a human, you can clearly see it's still a squirrel. So we can easily combine those differentiable modules into very interesting deep learning systems. There's actually one more interesting thing, which is differentiating physical simulators does not always yield useful gradients of the physical system being simulated. It might be a too long sentence, but let me explain what's happening here. So sometimes the gradients can just go wrong. Consider this example, and you have a rigid ball hits a frictionless ground, no gravity, no friction, fully elastic collision. It's easy to derive the relationship between the initial height and the final height, right? Because you know the vertical velocity is a constant before and after the collision because it's a fully elastic collision. You know, the final height and the initial height sums up to a constant, which means that if you evaluate the gradient of the final height with respect to the initial height, you get -1 because their sum is a constant. However, the differentiable simulator may tell you that the gradient is 1 instead of -1. So this is completely wrong. Why is that happening? Well, let's use a larger time step and see what's going on. Because our collision detection is still discrete, it's easy to see the final height actually races together with the initial height, except for a few discontinuities. So if you do the simulation, if you plot the final height, initial height figure, it's easy to get a blue curve, and you see a sawtooth pattern there. It has a correct tendency, but it has completely wrong gradients. The question is, how can we get the origin curve, which has both the correct tendency and the correct gradient? Well, it's actually pretty easy. We can just add time of impact, and then by adding time of impact to the system, to the simulator, the gradient is now correct. Actually, the time of impact fix is super important, and by doing that, the robot can learn much better from the red curve to the green curve. As you can see, without time of impact, basically it doesn't learn at all. With the time of impact fix, the green curve is doing a pretty decent job. Here's a comparison. Here's a visual comparison of optimizing with and without time of impact. As you can see, without time of impact, the robot doesn't move at all. What if we still use TOI for training, but we disable TOI for testing? The robots still work. So the funny thing is that when only forward is needed, without time of impact, the simulator is already good enough. But if you want to evaluate the gradients, then you do need more fixes to the simulator by adding time of impact. So takeaways here are differentiating physical simulators does not always yield useful gradients of the physical system being simulated. And maybe an easier description is a simulation good enough for forward may not be good enough for back propagation. So in summary, differentiable physics and AI, the combination is a very exciting new field, and we have explored Qin and DiffTaichi in this direction with very promising results, and we do enjoy research in this direction. There are many ways to combine differentiable physical modules and deep neural networks. You can use it to speed up learning. You can use differentiable physical modules to help close the sim-to-real gap because you can do system identification. You can improve the predictability by doing hybrid simulators where you have both physical modules for the physical part and deep neural networks for the data-driven parts. You can combine those two together. But be careful, sometimes a brute force auto-diff does not give you the correct gradient. Consider the rigid collision part we showed just now. And what is really important to me is productivity and performance. I really care about those two aspects about physical simulation, and especially how to make physical simulation as simple and available as deep learning is what I really care about. And my solution to improving productivity and performance is on developing programming languages and systems such as Taichi and DiffTaichi so that we can lower the barrier of writing high-performance differentiable simulators. So that's it. I would like to conclude this talk using a quote from Confucius: "Infrastructure is key to success. And by building Taichi and DiffTaichi, we do believe that we can make differentiable physics a more welcoming community, and it will lower the barrier for people to enter this exciting new field. Thank you so much for listening to this talk, and I'm happy to take a few questions.